Hey, so I think I went through this a while back, and someone requested that I videotape it. So I want to go through that real quick. For those of you that wants a video of the Zoom session that we had on signal encoding techniques. Okay, so what we have here is we have a message that is hi. It starts with uppercase H and lowercase I. So that is the message, which is the ASCII. The ASCII is uppercase H and lowercase I. Decimal is decimal value for ASCII uppercase H is 72, and it has a binary of 0, 1, 0, 0, 1, 0, 0, 0. For I, it's 105 for decimal, and binary is 0, 1, 1, 0, 1, 0, 0, 1. If you're not sure how I got the binary, you can reference either the ASCII conversion chart, or you can compute it yourself by looking out for the decimal value first within the ASCII conversion chart, and then you can formulate or you can easily derive or compute the binary or the conversion part. But if you're not good at, if you don't want to do it and you just want to know how the conversion is done, then you can probably let's go through this. So I have this little table over here that tells you binary conversion rules for 8-bit decimal computer system architecture. Since most computers generally by standard use the 8-bit architecture for as most of its uh, design needs. Obviously, there are higher bits than 8, but 8 seems to be the standard start off for most digital computer system architecture. So there are conversion rules that you should probably know. This should have been covered in data communication 1. I'm just going to go through briefly so you guys can get an idea of how the conversion is done. The first rule is you have to understand computer binary rules and then human decimal values rules as well. So with computers, obviously by now you should know that computers read information in binary, which is just 0 and 1. So there are only 2 states, and those values in terms of binary comes from the switching of voltage pulses, or voltage pulses or currents going through a circuitry, and it's either on or off. So what we have on and off, it's translated into the binaries. I'm guessing engineers figured if it's going to be on and off, because the circuits, the voltage or current going through a circuitry can only be on or off. So in that case, we can derive binary rules from that for computers in general, and that's what we have 1 and 0. 1 means it's on. If the circuit is receiving current, it's on. If it's not receiving any kind of, sorry, if it's receiving voltage pulses, then it's on. If it's not receiving any voltage pulses, then it's off, and that's 0. So 1 for on, current is flowing through, or voltage is initiated, and 0 for off, nothing is going through the circuitry. Okay, so that's where the computer binary rule stands from. And since in computing we start every calculation from 0, the The other rule is that you start every computation from 0. Since you got the binary 0 and 1, obviously 0 count as a value. So when it comes to 8-bit sequence, it's actually going to be from 0 to 7. So if it's 8-bit digital system, it will start from, in counting wise, it will start from 0 and end to 7. So if you look at some of these values at the top, the superscripts of these numbers, what I have over here, you notice that it starts from 0, 1, 2, 3, 4, 5, 6, 7. Okay, now the 2 just means that you have a binary sequence in 1 or 2, or in 2 states. So that's why you have 2 over there. So for the computer binary rules, 2 denotes the binary 0 and 1. And then the counting for computation wise starts from 0, and for 8-bit sequence, and it ends at 7 because 0 is also considered as a count. Okay. Now for human, it's more of decimals. Human beings count in decimal. Okay. We also start from 0 and go all the way. But when it comes to actual value, we so much don't represent the 0 within the calculation, which mostly when counting it's mostly from 1 something, 1, 2, 3, 4. You don't start from 0, blah 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 blah. So in decimal rules, which is in base 10 or base 10 value, uh, we started from 1 and then counting on up. Okay. Now let's go back to the computer binary rules again. So for 8-bit digital computer system architecture, the rule states that since you're dealing with binaries and it's only 2 states, uh, engineers or mathematicians have figured out a way to generate uh, or find a way to be able to convert from computer binary rules to human decimal rules. And the way they go about it is by representing the 8-bit sequence in logarithms uh, of base 2. Okay, and then for the decimal, it's actually logarithm of base 10. Okay, so computers use base 2, while humans in decimal use base 10. Okay, so with that computer rule in terms of the logarithm application or calculation or computation, uh, since we're dealing with 0 and 1 or 2 digits, we start the engineer or kind of mathematicians started with uh, the sequence in 2 raised to the power 0, which is, so it's like you have your binary raised to the first number within a computer counting system, which is from 0, and then 2 raised to the power 1, 2 raised to the power 2, 2 raised to the power 3, 2 raised to the power 4, all the way up to 2 raised to the power 7. Now, for a bit sequence within computer binary to be considered a decimal in terms to be considered to be converted into a human decimal rules. The idea is to switch as a bit sequence to as an on state. So in this case, if you were to switch this bit, this cells with all these ones over here, one meaning that it's an on state. If they were in on state, which is 1, then the value that it will take is 2 raised to the power 0, which will make it a 1 in decimal. Okay? If it's 2 raised to the power 1, then the decimal value it would take, if the bit sequence was an on state, going to be a 2 because 2 raised to the power 1 is 2. And when it's on within the third bit and it's 2 raised to the power 2, then it will make it a 4. Keep in mind, if it's on, if all the bits are on, then that's the values they're going to take on, which is the binary 2 raised to the, or the two states within computer binary rules raised to its counting sequence of whatever it is, of whatever bits arrangement you have. So in this case, we are within the third bit arrangement, and it happens to be 2 raised to the power 2, which is 4, or which is 2 times 2. Give like I said, if it's on. But if it were to be off, then it would have a 0 decimal value. Okay, we'll get to that conversion soon. I just want to emphasize on to get this values in the decimal, the human decimal rules to be effected in terms of conversion, all the bits, the 8-bit sequence has to be in an on state to generate this. And then once you add them all up, you would have 255, which will make up the decimal value of 8-bit digital computer system architecture having all of its bit sequence switched on, or having all of its bit sequence in on state. I hope I'm making things clear with this. So if the bit sequence are all switched on, their decimal representations are this, which is derived from the logarithm of its exponentials. So 2 for the 2 states that computer binary can take, and then the counting sequence within the logarithm levels, which is the exponentials or the superscripts. So 2 raised to the power 0 if it's an on state. If the first bit is an on state, and it's 2 raised to the power 0, then it has to be 1. If it's the second bit is also on state, then it's 2 raised to the power 2. Sorry, 2 raised to the power 1, which is 2 in decimal, and so forth and so forth. So 2 raised to the power 5 would be 32 if that bit, which in this could be a 6-bit sequence, is in an on state, you'd have 32. But in counting, it's actually in the fifth position, or has an exponent of 5, because we're counting from 0 instead of from 1. Okay, based on the computer counting rules. Okay, so that's how we got all these values. So obviously 2 raised to the power 7 is 28. And as I said, if you were to add up all the bit sequence for this 8-bit architecture, you should get a decimal value of 255. Okay, so with that rule stated for both the computer binaries and then the human decimals, you can use that concept of the on values and then the off values to basically handle the conversion between binary and decimal, or binary to decimal. So let's go to some few examples. So we have 72 decimal. What will be the binary sequence of it within an 8-bit digital computer system architecture? So the best way to go about that is, once you know this arrangement here and you have 72, then you know that the bits that needs to be switched on, which is the bit that needs to be an on state, and adding them all up to generate the decimal value of 72 has to be 64. So the seventh bit we have to be on, and then the fourth bit has to be on as well. So that's why you have 1 over here. And then when you do add them up, so you have 64 plus 8 gives you 72. So the binary becomes 0, 1, 0, 0, 1, 0, 0, 0. Are we following? Hope we are. Let's add more. So we have 105 now. So the question you should ask yourself is, how many of this 8-bit sequence needs to be switched, or which of the bit sequence within the 8-bit architecture needs to be switched on and accumulated or added together to give you 105 decimal. If you look at this very carefully, you know that for 105, 105 is smaller than 128, but it's bigger than 64. So obviously you cannot switch on the 8th bit, but you can switch on the 7th bit. So in this case, it's 0 here, but 1 here. Okay, so we have 64. 64 out of 105, you probably need about 41 more added to it to arrive at 105. So 41 more. So which of these other ones can we add? We can add 32. We can switch on 32. Switch on 32, so it becomes 64 plus 32, which is 96. So 96 out of 105, you have how many more left? 9 more left. So we can use 16. Obviously, 16 is bigger than 9. So obviously, the uh, fifth bit, which is a true to power 4, needs to be in an off state. But since we need 9 more, the fourth bit, which adds up to, or which gives a decimal value of 8, can be switched on. And then we need one. So we're taking 8 out of 9. We need one more, and that could be the first bit only that needs to be switched on. And the rest can move up with 0, or will be in an off state. So if you're to add it up, you have 64 plus 32 is 96. 96 plus 8 is what? 104. 104 plus 1, 104 plus 1 is 105. So the binary becomes 011010001. So it means that we only switched on the 7th bit, or the bits that were switched on are the 7th bit, the 6th bit, and the 4th bit, as well as the first bit, to give you the decimal value of 105. Okay. What about 252? Now, when it comes to big numbers like that, it's an easy way of going about it. We can go through the process and get it, but there's an easy way of going. I'm going to show you straight up so you can get it easily. If all the bits are switched on, if all the 8-bit sequences are switched on, you have a total decimal value of 255. So if we have 252 decimal and we need its binary representation, it means that we only have 3 that's left to add up to the full 255 decimal that will make all the bits switched on. It's only 3 that's left, plus it's 252 out of 255, which is what? 3. So it means that we only need the first 2, because the first 2 will add up to what? 3. That needs to be switched on. So it's only this and that needs to be switched on. And the rest has to be, sorry, what am I saying? Sorry about that. It means that all the from the 8th bit all the way up to the 6th bit needs to be switched on. It's only the last 2 bits that needs to be switched off to get a maximum decimal value of 53. You get it? Because it's 52 out of 55, which is 3. So 3 is the only less value that needs to be taken off to achieve the 252. So it means that this will be 1, So the 8th bit will be 1, 7 will be 1, 6 will be 1, 5 will be 1, 4 will be 1, 3 will be 1, but 2 and 1 has to be 0 because they add up to the 3 value that's minor, that's left, or that's less than the 255, which will add up to a complete on state for all the 8-bit sequence. So this is 255, obviously. So if you were to add up 128 plus 64 plus 32 plus 16 plus 8 plus 4 will give you what? 255. You can do the math. 128 plus 64 is 192, right? 192 plus 32, 192 plus 34 is what? 224, right? 192, 32, so 224. 224 plus 16 will be 224 plus 16 will give you what? 240, right? Am I correct? 192 plus 32 is 224. Yes, so 240. 240 plus 8 is 248. 248 plus 4 is 252. There you go. So you have that. So that's add up at 252. Okay, let's go to another one. We have let's try obviously 190. Yeah, let's do 15. Let's go 15. 15 decimal, so binary. So we only need if you were to go through this, we can't use 128 because 15 is way smaller than 128. So this bit has to be in an off state. So we can't use 64 either because 64 is bigger than 15. So that's 0. 32 is also the same, smaller, also bigger than 15. So off. 16 is greater than 15. So off state. But 8 is less than 15, so we can use it. So that should be an on state. 4. So now 8 out of 15, you have how many more left? 7. So 7, we can get 4. 4 out of 7, you have 3. Right? So 3, 2, you can get 1 out of this place over here, and then you have 1 more left. So this is 15 binary. We get, so that's your 15 right there, which is 8 plus 4 plus 2 plus 1. Okay? How about 240? 240. Well, like I said, when you do have big numbers like this in the 200s, you can always do a subtraction from the full state on or full 8-bit sequence being an on state. You can always do that. So 240 minus 255, you have what? 15 that needs to be switched off. So which means this 15 here, which is this one or this guy said, needs to be an off state to achieve the, and then the last 4 has to be an on state. So let's do the math. So 128 plus 64 is 192. 192 plus 32 is what? 192 plus 192 plus 32 is 2 224. 224. 224 plus 16 is 240. So you have the last 4 bits needs to be in an on state. And then the first 4 needs to be an off state to get you the 240. So anyway, so that's how you do the conversion for every 8-bit digital computer system architecture. Okay? Obviously, if you did have 16-bit or 32-bit or 64-bit or 128-bit and higher, 512 and blah blah, it would just increase. It would just increase. But the computer binary rules and the human decimal rule always always stand still. The computer binary rule states the 2 state, which is 2 in base 2, hence logarithm. So logarithm of base 2 with the counting from 0 to whatever that number is. So if it's 16-bit, it will count from 0 to what? 15, right? Since it's just 8, we have 0 count of within the logarithm base 2, so 7, or to 7 count. And a decimal value would just be the calculation of the exponents. So 2 raised to the power 0, whatever the value is. And that only applies when all the 8-bit sequence are 1 or are in an on state. So keep that in mind. These values only count. This human decimal rules only applies if the bit sequence are all in 1 or are all in an on state, which is 1. If they are 1, it means it's on. So that's how we got this. And then you can just use that to basically handle your conversion from decimal to binary and binary to decimal, the same concept. Okay, so with this, you were to go back and forth, either from decimal to binary or binary to decimal. Okay, now let's move on to the actual uh, uh, discussion or examples for the signal encoding technique. Now, I had to go through this because of the fact that the signal encoding technique requires you to know these two conversions between decimal and binary, because the signals are going to be within a sequence of binary forms. So whenever you have a message, what a computer does, it actually reads that information as an ASCII and then looks up the conversion chart, which you already know by now. Or if you don't, there has to be a copy somewhere within the slides. There is a copy in the slides that you can go through, or you can even Google it online. So I look for the ASCII conversion chart. You get a list of them. And then so the computer looks up the ASCII character, which is all the various key characters on your keyboards. Like I said, keep saying the numbers and then the alphabet as well as the non-alphanumeric characters you see on your computer keypad or keyboard are considered ASCII characters, and they have decimal value that attach to them, usually within an 8-bit sequence architecture or computer architecture. So with that, the computer was to generate the binary format. But the computer doesn't go through the calculation. It just has a table. I mean, obviously, it can do the calculation based on the program that's been designed for it. But there is a chart that's embedded on most computer circuitry boards on a memory chip somewhere that has the ASCII converted chart. So all the computer does is go through that. So if it sees that you type an uppercase H, it'll go through the table or the chart and then look for the corresponding decimal value for H, which is 72, as well as the corresponding binary. And then it uses that to generate the signal. Since computers can only use signal to transfer information, but a human being requires more or less the decimal or the ASCIIs. So they designed that